Hopefully you can see the slides. So thank you for inviting me, Eugene, and the organizers, and it's my pleasure to share with you some of the work that we're doing, leveraging artificial intelligence, both in applications to molecular and clinical data. And I'll use Alzheimer's disease as a case study here. But before I start, I always like to say why I'm excited to be a computational biologist today. And one of the reasons is that there's tons of data out there. There's publicly available molecular data, and these are some examples of these resources. As the cost of technology has gone down in the last 20 years, we're coming up with creative ways to profile individuals, both healthy individuals and individuals with disease. And those include genomics, transcriptomics, looking at antibody repertoire, proteomics, as well as figuring out how to integrate all of these measures. And finally, we have access to real-world electronic medical records data. This is information that gets captured when somebody goes to see a doctor. And these include diagnosis codes, lab test results, procedures, and so many others. At UCSF, we have access not only to electronic medical records data from UCSF, but across the whole UC system. And those data are available in a de-identified manner for research purposes. So the goal of my lab is to figure out how to integrate these data all together using both statistical approaches as well as machine learning to better understand disease. So I'll give you two examples today in ways that we're going from molecular data to clinical data in the context of drug discovery, as well as how we go from clinical data to molecular insights in the context of disease predictions. And again, we use a wide range of computational approaches using both statistical measures and artificial intelligence. And the goal of all of this is to come up with hypotheses for discovery. In the context of drug discovery, one opportunity is drug repurposing. The idea behind drug repurposing is that we can take compounds that are already FDA approved and identify new uses for those drugs. It's expensive to take a drug and bring it to market, and about 90% of drugs fail in early development, where drug repurposing can solve some of those issues. So in my lab, we've developed an approach to use gene expression data. This is a molecular measure of which genes are turned on and which genes are turned off to better understand new therapeutic strategies and make therapeutic predictions. We've applied this approach. This is actually stemming from my graduate work with Dr. Butte to a number of different conditions, including dermatomyositis, IBD, cancer applications, as well as pregnancy outcomes. But today, I'd like to give you an example from Alzheimer's disease. So this is work by a very talented graduate student who was jointly advised by myself and Dr. Yadang Huang, Ali Taubes. And what we aim to do is to try to come up with a precision medicine therapeutic approach for Alzheimer's, specifically looking at patients with ApoE44 genotype, which is the biggest risk factor for Alzheimer's disease. We gathered publicly available data, tried to understand genotype-specific signatures, and then we queried those against a database of drugs and drug expression profiles. In this query, we were able to identify bumetanide as a potential therapeutic prediction. And this is just showing the fact that the disease signature for Alzheimer's ApoE44 individuals is reversed back to normal by expression signatures of a therapeutic called bumetanide. So bumetanide is a loop diuretic that works by decreasing the reabsorption of sodium by the kidneys, and it's used to treat edema and hypertension. There were a number of animal studies carried out to help validate this finding. So this is a test called a memory impairment test, a water maze, where an animal who has a memory impairment is placed in a water bath, and the animals, as I understand, do not like to be in water, but there's a hidden platform that allows them to escape. So what we measure here is escape latency. And this graph shows that with treatment with bumetanide, even animals, ApoE44 animals, who have some delays, go back to normal after treatment. However, we wanted to validate this in addition to looking at animal data with real-world clinical data. So we went to the electronic medical record data at UCSF. At that time, we had information on about 1.3 million patients, which include a number of different measures, including diagnosis codes, lab test results, and medication orders, as well as others. And we wanted to see whether patients on this drug, patients who are already taking bumetanide, have a lower prevalence of Alzheimer's disease. So we queried the electronic medical record data for patients on the drug already, on bumetanide, and got about 5,500 individuals. We focused on individuals over the age of 65, and we compared them to patients with similar characteristics who were not on the drug. And we were able to show that patients on bumetanide, shown here, have a lower prevalence, a significantly lower prevalence of Alzheimer's than matched controls. Then we repeated the same procedure in an independent electronic medical record at Mount Sinai. So this really gives us an example of how you can use molecular data to make predictions and then use clinical data to help validate them. Now we've been extending this work using electronic medical records in many different directions. This is work led by Alice Tang, who's a very talented MD PhD student in my lab and was published last year in Nature Communications. This is a visualization of all the Alzheimer's disease patients, as well as a matched control cohort at UCSF and Mount Sinai. Each dot here is a patient. They're based on the clinical profiles of these individuals. The red dots are Alzheimer's patients. In blue, we're showing controls. And you can see that we can separate these out, which means we can now start applying machine learning to these data to try to identify which patients are at a higher risk for disease. We can look at comorbidity networks, which diseases are associated with Alzheimer's. And of course, we see things that make sense, like mild cognitive impairment and dementia, but we also see others like hypertension, hyperlipidemia, urinary tract infection, and all of these are potential risk factors. On the other side, we can see diagnoses that are inversely associated and might have some sort of a protective association, and cancer is one of those. We can see that the majority of these validate across independent electronic medical records. We can build upon this and start building predictive models. And this is work that is currently available as a preprint on bioRxiv and is under review in Nature Aging, also led by Alice. What she has done is now she's taken these cohorts and she's able to predict using machine learning, classical machine learning approaches, which patients are more or less likely to develop Alzheimer's 1 year, 3 years, and 9 years prior to diagnosis. You can see that the models improve, the prediction power is better and better as we get closer to the diagnosis date, which is expected. And finally, we can start looking at features which are associated. And these are just some examples. And again, we see similar things coming up like hyperlipidemia, osteoporosis, dizziness, and many, many others, vitamin levels, memory loss. We can further then use this clinical data to go back to the molecular space and understand what are the underpinning genes that might be responsible for some of these associations, which we've been exploring in the context of the links between Alzheimer's and hyperlipidemia. And of course, one of the links that comes up here is expected, that's ApoE, but we can make new discoveries as well. We can further validate some of these associations across larger cohorts. So this is showing survival analysis, which validates the hyperlipidemia and Alzheimer's disease link that I just showed to you across the whole state of California. And we've done the same for the link between osteoporosis and Alzheimer's. So I hopefully gave you a flavor today of the way that we can use data, both molecular and clinical data, and integrate it to understand and inform both diagnostics and therapeutics in the context of Alzheimer's disease. We use both statistical approaches as well as more advanced machine learning And I'm excited to continue the discussion with everybody. And hopefully I opened some avenue of ways that we can use this data. This is the team, and I'd like to acknowledge everybody working on the projects that I mentioned. And this is us here. And I'll stop there.
Thank you very much. Thank you very much, Dr. Sirota. We do have questions for you, but we will broadcast them after all the presentations. Switching to Dr. Solid with his presentation now. Thank you very much.
Thank you, Eugene. Good morning, everybody. What an exciting time to be in healthcare and medicine. I never thought that we will be talking about that so early in our evolution of large language models, but we are. And if you look at a lot of the evolution over the last 20 years, it used to take a lot of time for us to get new feature. It's used to take a lot of the efforts and validation to reach human performance. And now all of a sudden, right, in 2017 with the transformer, we're starting to get magic boxes. We started to get something that can understand the language, understand the pictures, and frankly, change a lot of the way we're doing and building things. So the speed of innovation started to rapidly accelerate. And when you see, and by now, and that's the beauty of the area right now, is by now this graph is pretty much outdated, because every day we see yet new gain in a new data set or a new test, or additional foundation model has been tuned for specific use cases. So the speed of innovation is being rapidly accelerating. And even now, when we look at the previously gold standard test for human performance, we can see how models over the last 12 months, 18 months, now reaching performance level from human and even above. So what we look at, and the way we look at that at UC Davis and on national level, is we should keep expecting the rapid acceleration. And for the long time, the feedback from clinicians was, yes, but those are machines. Humans prefer not only human touch, but we better communicate empathy, and we can better establish rapport, which is also not come out to be truth. We actually see where a large language model can potentially better communicate empathy compared to the regular busy overworked clinicians. So the way we look at a lot of the things and build currently with LLM is sky's the limit. There is so many opportunities, but we need to look at what's currently is easy verifiable, what's currently aligned with FDA regulation of medical devices, where we can safely continuously monitor the performance of a machine and models. So the way we try to approach is by building on a thing that's good with large language models and trying to create scenarios where we can test experiment around things that may be very attractive, but still a little bit farther in the future. So what we see is there is tons of positive. For the first time, we have a tool that actually can document for us, not only clinically, but administratively. We can personalize the information. We can create multi-source summaries. And even 10 years ago, we've been talking only about, can I just get the data? Now the data can not only be pulled, but actually summarized for you. We can improve automation beyond just creating a simple RPA workflows. And for the first time, clinicians can be liberated from the tyranny of EHR, where you can actually document your voice directly where you're the patient. But of course, none of that is coming with some negative downsides. And one of them is we still do not really know exactly how the model thinks. We still may encounter hallucination or hypothesis. We still may have a lot of the probabilities of inheriting basis in the model themselves, just based on the notion of the data set they've been trained on. And privacy is still under question. And of course, we cannot spend on a negative environmental impact. So with all of that, why do we believe that it's a game changer? And I'll start with the last. Workforce being a biggest problem in the healthcare. We scale every technology with additional humans. And that's one of the first technology where technically you can start solving a lot of a technical task without purely extremely technical talent. I can actually now start empowering diverse talent to work with large language models to solve the problem that's before require very specific level of education. And it's easy. A lot of that is API level development, is based on a relatively simple interaction, versatile and easy to experiment. So next, I'll talk about 3 large archetype of interaction we're working on. It's not being to be comprehensive, right? But I think at least it will give you an overview of the direction and the type of the use cases we're looking at. One is non-clinical deployment. Specifically, if we pull and create a system around the knowledge access and chat with your data, answer Q&A and the policies, what can happen? And our guess here is by enabling this information that's stored in our SharePoint and the documents and a spreadsheet all over our intranet, we actually can add efficiency to our teams. Because sometimes finding a very simple answer that's documented somewhere takes days or weeks. And it's relatively easy for people to ask the question. You just ask the question same way you will ask on a team. And that also will help us to find information that's currently available, but it's not true. So chatting with non-clinical data inside the infrastructure. The second big archetype is where large language model used to generate content or information, but we have a human validation in the loop, right? And a great example of that is us currently looking at after visit summaries and trying to create additional version in multiple languages that's without large language models possibly would never be translated or implemented, right? So we create the drafting after visit summary, then using large language model, translating it to the language, and then use our human dedicated translator services to validate that. And here, of course, we hope that not only the speed of creation after visit summaries, but actually the availability will help us to increase inclusivity and patient engagement, ultimately strengthening the trust in the healthcare system. And the last is personally exciting to me as a clinician informatician is something that's combined, right? Like our efforts of interoperability as well as advancing large language models, where we try to start building smart on fire application that can perform certain action, right? On the clinical. A lot of that's are not yet in production, specifically not available outside of the research, but the direction is there. So when you have fire-enabled application and you can pull the data in, you can summarize what's going on. You can get some rapid insights or potentially get tailored clinical decision support. And I see where a lot of the application like that will be built in the future. But again, everything comes with the risks, right? And here, what you see is on every step of the visit, from appointment to after visit summary, you have significant risks that you need to think about when you develop a large language application. And some of them will be solved by the platforms in the future. Some of them right now, as an early innovator, you have to think about yourself and you have to solve with your own team. So over the next 12 months, our main focus is actually building infrastructure. We know the use cases will be painful. We know this is possibly one of the most impactful technical tool we'll see. So our goal is to enable the community across the UC Davis on getting access to this tool. We also will empower collaborative learning across the institution through various networks. And we want to do the pilot programs. We already have several target pilots. I talk about it. We're planning to extend. And we want to share best practices. We want to learn from collaborators. We want to talk about our experience. But ultimately, we want to empower users all across our clinical and technical communities to learn from this technology, to share the best practices and cultivate in-house generative AI specialists that can actually help us to safely deploy it and hopefully help our clinical deliveries and the clinical care move to the next stage. Thank you.
Thank you very much, Dr. Solid. Appreciate it. We have, I think, one or two questions with regards to your presentation, which we will turn at the end. Dr. Shah, it's your turn, please, sir.
All right. Well, thank you. Thank you to Marina and Yohani for the wonderful talks. So I'm not going to show any slides. I see about 140 attendees. And for those of you that have a writing instrument in front of you, a pen, paper, or an electronic gadget, we are going to use that quite a bit. Otherwise, you'll have to rely on your imagination. So it is not a question of whether language models will be used in healthcare, or I like to think of them more as sequence models or token models. The question is how. And in order to sort of ground our thinking, I would ask those of you that have procured a writing device to draw a triangle on your favorite information gathering gadget. And on that triangle, I want you to name the upper vertex as creating models. And we'll stick with language models for now, but we can expand that. On the lower left, I want you to label that vertex as verifying benefits. In the lower right, we're going to label that as deploying or incorporating in production IT systems in healthcare. So now we have this little structure in front of us. And if you ask yourself, amongst all the media hype and all the papers coming out, there's a lot of model building going on. Lots of it. There's something like 1,500 publicly available language models hosted in some sort of API somewhere. To OpenAI's credit, they've turned ChatGPT as a synonym for large language models, but even behind that web application, there's 2 language models, and there's speculation that GPT-4 could in fact be 8 models. Who knows? Nobody knows. My point here is that the manner in which these models are built is mostly a dark art. We don't know the data mixtures they have been trained on. And the anecdote I like to mention is the web app ChatGPT became possible because of instruction tuning of GPT 3.5, the language model underneath it. On OpenAI's own website, there's examples that say the vanilla language model, when posed with an instruction, explain the moon landing to a 6-year-old, might respond with the words explain gravity to a 6-year-old, because those are distributionally the most similar sounding words. Humans, most of them not in the United States, trained the model by giving it examples of good responses that align with our expectations, or picking from a bunch of model responses and rank ordering them, saying which is the best one. On top of that, you learn another model that can then automate that process. That's reinforcement learning with human feedback. The point being, without that labor of instruction tuning and aligning the models with what we want them to do, those models didn't do anything that we wanted, not even something as mundane as chat. So the question I pose to you is that in the enterprise of building models, language models for medical use, where have we put in the labor of doing such instruction tuning? Have we verified the data mixtures? Like we're so excited about zero-shot learning and few-shot learning. How are we to convince ourselves that the output of few-shot trained models will not be biased? What is our strategy for that? Where is the instruction tuning data set that tells us that for the instruction, summarize this patient's medical record, the output produced by the model is verifiably correct? We don't even have 1,000 such examples. For web chat, it was trained on hundreds of thousands of examples. So that's the issue around the top vortex, building models. Now, if we go to the lower left, the one I had you label as verifying benefits, our current mechanisms of verifying benefits are about as absurd as sending a self-driving car to the DMV and having it take a 20-question multiple choice test and certifying it for driving. We send GPT or MedPalm or whoever to take the USMLE exam, and it passes USMLE 2, and we say, yep, you can now go see patients. Not very different from that absurd car example I gave you. But that is the absurdity we are allowing in our excitement about adopting these things. So I think we as a community need to come together and say, what are the metrics by which we can verify whether the presumed benefits of few-shot learning, being able to provide 24/7 asynchronous advice, being able to summarize documents, how are we going to verify that? And more important, if it makes an error, what is our strategy to catch it? So that's on that vortex. And then finally, in order to get these things into IT systems, for those of you who are familiar with the hospital IT infrastructure, I mean, it's a great way to time travel 20 years back. We're talking about a 15, 20-year technology leap in a matter of 6 to 7 months. It's going to push IT departments really hard, both in terms of talent and skill acquisition, in terms of platform acquisition, and in terms of figuring out, when is it worthwhile for a bunch of health systems to come together and create open source models, very similar to the Civica RX, which does generic pharmaceuticals for health systems. And when is it worthwhile to go to a vendor and pay, 20 cents per interaction? And we don't have a strategy around that either. So while the excitement is real, the 2023 Gartner hype cycle puts generative AI right at the peak of the hype. We are going to go through that trough of disillusionment. And I think before we start sliding down, I think it's important for all of us to figure out how are we going to square this triangle that I just laid out for you, that this building of models, verifying their benefits, and getting them deployed. We need a systematic strategy to traverse this instead of just doing projects, because otherwise we're going to end up with a condition I love to christen as pilotitis. So with that, I think my 10 minutes are up, and we can proceed to the next phase.
Thank you. Thank you very much, Dr. Shah. Appreciate it. I think you touched on some of the points that have been asked from the group here as far as questions are concerned, but let me just read out a couple, and then we go from there. So as a question from Karen, how does AI help overcome the lack of data standardization on structured data sets in EHRs for research and discovery? And I will echo that, if I may. And I think you touched on it in your speech here. What are your opinions about possible data sharing models to make it possible for clinicians to react quicker and make decisions faster? I will probably mention just one that I'm aware of, which is the one described in the Mayo Clinic today, as far as their sort of approach of making data available to third parties. But if you could give your opinions on these, that would be great. Thank you.
Marina, you want to go first?
Sure, I can start. So I think one important aspect is whether this data sharing is happening for research or implementation purposes. In the context of research, there are various standardization tools. For instance, a lot of the data across the UC system is standardized in OMOP, and many others are as well. That way we can start building predictive models, for instance, at UCSF, and then port them to other UCs, to Stanford, to other institutions. And we've done that quite a bit in the research setting. In the context of implementation and clinical sharing, maybe I will turn it over to the other presenters to comment on that. But in the research setting, there are rules, and there are systems, and I imagine the generative AI and AI methods can only improve them. But I'll let others comment on the implementation side.
Yeah, so I'll just make two quick remarks. One, abstraction always been extremely painful. So manual abstraction is horrible and leads to a lot of errors, right? So I think that the first and the easiest benefits of that is simplified powered abstraction by sequencing a large language model, right? And then don't forget that a lot of our current interoperability in a Fire, bulk Fire, or Smart on Fire ultimately are web applications, and large language models are good in writing code, right? So I think those two additional tailwinds will help to open up a lot of data sources.
Yeah, I would sort of close out saying shedding data has never been a technology problem. It's always been an incentive problem. LLMs are not immune from that either. So unless we figure out incentives for data sharing, it's still going to be the same story again.
Yes, and I would agree. It's kind of a interesting observation today. The stick versus the carrot, and top down from and bottom up. But I think that's a subject for a webinar on itself altogether. So thank you.
Sorry, I'll make one more comment about this. One place where I did see things work out quite well was in the context of COVID. Cerner, for instance, pulled electronic medical records data across all their centers, 87 centers, and they actually made it available to researchers for free in the context of the COVID-19 patients. And it was an amazing resource. My team was able to get access to it, and we were able to test some of our therapeutic predictions in that data. So I think when there is an incentive and a goal to share data or a common problem that everybody's trying to solve, I think technically it's feasible to do that. And that was just one demonstration that came to mind.
Thank you. Regardless of the fact that this is a subject dear to my heart, I'm not going to hijack this and just move on to the next question. So we have a question from an anonymous attendee regarding AD, and I assume we're talking about Alzheimer's. How much accuracy are you seeing in predicting AD, and how early? Additionally, how is AI helping in any early preventive measures?
Great question. So in terms of accuracy, we're seeing about 0.7, 0.8 AUC. And we go from, as I said, like a year before diagnosis to up to 9 years. And of course, the earlier you try to predict, the worse the models perform. But we hope that this, together with some of the molecular efforts, can really improve diagnosis for Alzheimer's moving forward. Currently, these are not implemented in the clinic. One area that I didn't mention at all is running AI and predictive models on imaging features and MRIs in the context of Alzheimer's. And I think in my mind, it's integrating the clinical models together with the imaging, together with some of the molecular measures, is where we can have the most success. But we're still in the research space here, and I hope we can move towards implementation in the near future.
Well, yes, and given that the population is not getting younger, it's an issue that really has to be a great focus. And thank you, Dr. Sirota. Next question on Gen AI for chatbots for member interaction. Where do you see physician adaptability? How much resistance do you see from physicians in trusting outputs for Gen AI models? I think there are two slightly separate questions rolled into one, but I'll let you guys comment on these if you could.
Happy to start. We are very early in our journey, right? And I think both Nigam and I covered like a different part of the same equation, because you need more evidence, right, to actually generate answers, right, and understanding and a lot of validation, right? You can't just validate continuously in the lab, but a lot of those tools right now are not ready for the scale deployments in prod, because we still have so many answers. So the proper, piloting, avoiding pilotitis, but on the same time, validation of a hypothesis where you actually create learning examples and you engage the proper stakeholders to learn from that, generate trust, right? So we need to come up with this good way where we are fast enough to show the progress because we cannot deny our clinician being under administrative burden for far too long. So now they're ready to try anything to make their life easier. But on the same time, we cannot avoid, right? Creating a proper safety layer to validating every action you do, because after all, we're still liable for things we document, and for clinical care, we protect. And same way as I just use ChatGPT is not an argument, right? In a legal practice, when you make an error, it will not be defendable in a clinical practice in the long term.
Yeah. So I'll answer this slightly in jest and with an analogy, mostly to make the point across. So it's an often cited refrain that you shouldn't go grocery shopping when you're really hungry, because you end up buying a lot of junk food. And so think about it. If our physicians are overly stressed, they're ready to try anything, why would you have such an overworked, overstressed person making the choice about what to buy? You could end up buying junk food. Don't go shopping when you're hungry. And so I mean, it's partly in jest and partly like I'm serious about this, is that I think we put too much expectation on the physician, who's an individual trained in medicine. They go to the school of medicine. They do not go to the school of healthcare. And I think it has to be a multi-stakeholder conversation where the physician is one party in this delicate, complex network, which involves nurses, pharmacists, patients. God forbid, nobody talks about patients usually, in order to make the decision about what should be used where. So I strongly urge everybody to not go shopping, not go grocery shopping when you're really hungry, because you might end up buying a lot of junk food.
Thank you. Thank you very much. Actually, I had a question, but this is maybe for later, because this is a very kind of sensitive point with regards to how can AI today, and I think you're addressing it, how can AI today impact the work of the, let's call them the frontline workers, the folks that are in the primary care space, in the family care space? What do they get out of it immediately today, and how does this evolve into the future? Because I think we're looking at some kind of a more moderate approach, after this hype cycle that you described, before we start going into the trough of disillusionment. So yeah, that'd be a great subject to discuss further. With regards to the next question, I think a lot of the questions revolve around the standards. But let me just go through the list here. Are there any AI-friendly data collection standards so that quality data can be collected globally? Anybody wants to tackle that?
I think there's just way too many data standards. So I bet there is one that allows you to collect information, say, across, your U.S. and Australia, and then there's probably another one for U.S. and New Zealand. I mean, so the thing about data standards is that there's way too many of them.
Thank you. Let's see. I think there are a couple of comments here. Thank you, Dr. Lee. Do you see LLM AI-based abstraction efforts being done in a scalable manner now?
I'm not sure I follow what abstraction efforts means in this context.
Right. Well, we may need a clarification on that, and Dr. Lee may want to type that out later. Let's see. As a neurologist, I'd be very curious how we can use these AD models to enroll patients into clinical trials earlier or get access to the new FDA-approved meds. Also curious about the racial ethnicity differences picked up in your model.
Oh, this is a great, I'm assuming that this is for the Alzheimer's example.
Yeah.
These are all great questions, so I can jump in. So in terms of getting patients enrolled in clinical trials, absolutely. If we are able to identify which patients are more likely to develop Alzheimer's several years before they actually do, or before the onset of symptoms, those patients could potentially be enrolled in clinical trials early. In terms of the racial and ethnic background differences, of course, I had 10 minutes. I didn't have time to talk about it. But we have a paper that was published this year looking at comorbidities specifically stratified by different racial and ethnic groups across the state of California. And our patient population is fairly diverse. Not, we should strive for better, but at least we have some inklings. And these relationships are different. Actually, in Alzheimer's disease, women and men have vastly different disease manifestations. So we're studying sex differences using both molecular and clinical data. And actually, some of our therapeutic predictions work. We're validating them in male and female mice, and some of them work better in male mice versus female. So there are vast racial and ethnic as well as sex differences in Alzheimer's, but also in many other conditions. And really, we can use clinical data to study these differences. We have a long way to go to have a representative population. What does it mean? Representative of the US, representative of the world, but we're taking steps there. And these are really, I don't have all the answers, but these are really important questions to ask, and we're working on it.
Thank you. Let's see, if an organization is just starting, where would the panel suggest you start the conversation about use of generative AI? And I assume this is a healthcare question.
Like with any technology, start with a problem. Very often the whole fact that we now have a new technology is not a reason for you to start talking about it. Go back to your problem, define your data sources, your workflows, and see where in a validated manner, right, generative AI tools may be helpful.
Yeah. So the only thing I'll add to that is define your success and failure. Often we have a deep understanding of the problem. For example, I'll use the Epic in-basket problem. A lot of people viscerally feel that problem on a daily basis. But what does success mean there? Does success mean we have a happier physician provider? Or does success mean that objectively less work has been done? Or does success mean that more messages have been answered in the same unit amount of time? Or does success mean that that work has gone away and you can see 2 more patients? Those are very different success criteria. And unless they're declared up front, we can't be sure whether we succeeded.
Thank you. Let's see. Well, questions are coming, more questions are coming in, so let's work through them. Multi-stakeholder conversations are truly important but difficult to implement. What suggestions do you have to bring the ecosystems together at both the local level and national level? Do you think organizations like HIMSS in Northern California, institutions like Stanford, UCSF, UC Davis can help? If so, suggest some specific ways.
Oh, that is a great question. Something that I struggle with on a daily basis, because right now there's so much excitement that every clinical specialty, every professional organization, journals, all want to become a leader on how to shape the adoption of generative AI in healthcare. And you can only have so many leaders. Somebody has to follow. And so what I'm watching for, and I don't have a prescription for you, given that it is what I'm watching for is what is the entity that is able to crisply define what is the benefit that they hope to accomplish, and do they have an objective metric of success? Those are the people I'm willing to follow. And currently, one of the groups that I'm part of is this Coalition for Health AI, where we're starting to put out a national blueprint of how can we have a network of assurance labs, national AI assurance labs, where you can go with whatever solution, generative AI or your logistic regression or random forest, and ask, does this have this benefit that I've pre-specified? Like, we do that for trials, we do that for a lot of things, even for observational studies. We register them and we specify what is it that we're hoping to do. So I think anything that goes in that general direction that forces you to pre-specify what is the problem you're solving and what does success mean, and then gives you an objective way to test. If anything meets these three criteria, that's a good group to hang out with. And it could emerge from anywhere.
Anybody else wants to make a comment on that? Well, considering that it took, how many decades to move into the interoperability standards that we're discussing today, and considering how AI is spreading, that sort of foundation of standards need to be found really quick before, there's going to be a group of individuals like they recently were, making statements in front of the congressional hearings, explaining why there is such a big problem with information access and search parameters. So that can happen. Let's see. In your experience, how much success are you seeing in gathering and using lifestyle-related data apart from wearable devices, RPM devices? Anybody want to tackle that, or?
It's an interesting question. I'm not sure it's directly generative AI related, but from a clinical, wearing my clinical hat, relatively little, right? It's not about the collection, it's about the implementation that's into the clinical practice and insight, right? And you may collect, but if no one truly modify care around that, then what's the point? And it's not aggressively part of our clinical practice guidelines. So.
Yeah, I think the question was basically towards, is this some sort of augmentation to the already other collected data from EHR systems and so on and so forth? And I think you're addressing that it's another subset that's going to be added to the mix, but only time will tell and models will tell what that ends up going to be. Let's see. Has generative AI been used for disease stratification and other complex diseases such as IPF, ILD, etc.? I don't know if anybody wants.
I can mention, I think it's been applied across the board. These computational and AI methods are being applied in different disease areas. And my own team, as I mentioned, we work on Alzheimer's, but we work on women's health more broadly. So we work on pregnancy outcomes like preterm birth, on autoimmunity. So these are all examples, but I'm sure there are many other teams working across all clinical domains, or many of the clinical domains.
Yeah, I'm going to echo one of Yoheni's past comments. It's not about the technology. So, for example, I'm assuming IPF is idiopathic pulmonary fibrosis. We can stratify that disease based on, say, a molecular marker such as monocyte count. You can stratify the disease based on some complex deep neural net. You can stratify the disease using a language model and the patient's past medical record, what have you. But what I would encourage you to ask is, by any of those mechanisms of stratification, are you able to do something different for the patient? And by doing so, does it lead to somebody having a better quality of life? Because I think what happens is that a lot of things are possible, but because we can group and sort and classify, doesn't mean we can do something about an individual being in a high risk or a low risk category. And so I tend to ask the question, whatever mechanism is used to risk stratify, what net new action or different action does it enable you to do? And if not, from a functional standpoint, it's no different from your previous classification regime.
Thank you. Question, how do you tackle the biases in large language models when implementing in a clinical environment? So I'm going to put a plug here for Stanford because I took a class there on that. There's a description on addressing biases, but I let people smarter than I on this subject to address it. Please.
So on biases, I would urge you to not use that word and unpack it into its two constituent parts. There is a conceptualization of that notion in the form of, is there a systematic difference in the model or algorithm's output for humans belonging to different subgroups. That's one notion of bias. The second notion of bias is, as a result of using some model's output in the light of some policy, is there a systematic difference in the accrual of some benefit to humans that are in certain subgroups? And we need to untangle those two. Often it happens that, yes, there is a systematic difference in the model's output, primarily driven by the data it has learned from, but there's no evidence that there is a systematic difference in the accrual of benefit. One of the most commonly used algorithms to guide decisions in the US is the pooled cohort equation, also known as the Framingham equation. It's the next generation of it. It is biased by this definition for 40 million Americans. The equation produces a systematically different output for people belonging to certain subclasses. But it's of not much consequence because nobody gets denied a statin because your risk was 7% and not 7.5%. And so we never get bent out of shape about the pooled cohort equation being quote unquote biased. So I think I would encourage people to untangle those two, because there's a lot of sensitivities around that. And the majority of the times, these algorithms are making patterns inherent in the database in our face. And when we don't like what we see, we say the algorithm is biased. But the root cause is something quite different. And so if we untangle them, we can take some action to mitigate those disparate consequences.
Thank you, Dr. Shah. I know anybody else wants to lend an opinion on that? No. Okay.
I think that just a quick comment is in a time where we learn from all of the internet data sets, right, and cannot properly quantify our data sources, very hard to expect the models not to be, biased or anything else. We need to get better with the sources, disclosing the sources, learning from that, and I think that will be like part of our learning exercise.
Thank you. We have
first we have to quantify them by having a clear test. And that's my biggest thing with all of these language model solutions, right? Like, where's the test?
Well, thank you very much, dear speakers, and all the participants.